this solenoid acts like a magnet, and so we call it an electromagnet. It's a magnet that, unlike a piece of iron that we can make a permanent magnet, this thing only is a magnet when there's current flowing through it. And actually, electromagnets are used a lot to move things around, to switch things. And usually what happens is, instead of leaving an air core here, we take a bar of iron and we put the bar of iron in there. And that's because when we do that, we cause the iron to actually become a magnet too, and we increase the strength of that electromagnet by lots and lots and lots. And so this is an example of maybe a switch that can be used to, or a circuit that can be used to ring a bell. And so essentially, what you do is you have your switch, you close that pushes a current through this solenoid, that acts like a magnet, grabs that iron bar and pulls it through, smashes it into the bell, then you release the switch is undone, and so then the spring is going to push that back. And so you get this electromagnet that can pull that bar through, smash into something else, and it's just a solenoid. It's just current moving through coils of wire, but all of those coils add up and can make a fairly strong magnetic field. Now, there's some other cool things that we do with this. Because there is a force acting on wires that move through, that are cutting electric field lines, or magnetic field lines, we also get things like motors and speakers. So this is going to be kind of an in-depth view of what's going on inside of a very simple motor. So what we have, we're looking at a front view. So we've got this coil of wire, current flows into one side, up and around and out the other side. And then this whole coil is put into a magnetic field, nice uniform stationary magnetic field. And because of that, there are forces on these wires. Now, there's not any force up here because the force up there, or the angle between the current and the magnetic field is zero, so the force is zero. But here, these things are perpendicular to each other. And that force, right, we put our fingers in the direction of current, so we point them up, we curl it in the direction of the magnetic field, and in order to do that, we see that there is a force into the page right here, and on the other side there's a force out of the page. And if this loop of wire is free to rotate about its axis down the middle, then these forces are going to cause a torque. And here's that same thing, but now we're looking at a top-down view. So now we're looking down from the top. Here's our axis of rotation, and then here's the force over here, force over here. And this, remember, a torque is equal to a force times a lever arm. Well, our lever arm is half of this distance b, so b over 2. So force times b over 2, plus there's another torque over here, that force F times b over 2 again. And so assuming that the current is the same on both sides, which seems to be a safe assumption, and the magnetic field is uniform, seems to be a safe assumption, then the force is the same. So this is F times b, gets us that torque. But if instead of just using one coil of wire, we use lots of coils of wire, so several, we use n coils of wire, then what we actually get is the torque is going to be related to NFB. Now, this is interesting because it's also going to be, we've got the length of this wire in here, right? Oh, so there should be an L here and an L here. Times B times L. Well, L is going to be this length here, and B is that here, which is the area of that. And so what this loop or coils of wire have is what's called a magnetic moment. And that magnetic moment is perpendicular to the face of the coil, and it's equal to the number of coils times the current in the coils times the area. And that area is really just this B times L. It's the area of that loop. So let's look at this again. Okay, the forces on opposite sides will be equal and opposite. The field is uniform and the loop is symmetric. There will be a torque. Now, what happens if the loop gets up to here, right? Well, then the force is this way and the force is this way, and so there is no torque. So if there's 90 degrees between the loop of the wire and the magnetic field, then we're not going to see a torque. However, if as long as that angle is not 90 degrees, then there will be a torque on that loop. And so we're going to see that DC motors make a cool little use of this, right? So the magnetic torque is given by this thing, the magnetic moment, but that's just N, the number of loops, I, the current in the wire, and A, the area of the loop, times the strength of the magnetic field, times the sine of the angle between the loop and the magnetic field. And then, like I said, that's the magnetic dipole moment, and it's number of coils times current times area of the loop. Okay, this is a motor. So, well, okay, this is a model of a motor. What's going on here? Well, we've got a magnetic field that's emanating from the North Pole to the South Pole, and that's putting a torque on this thing. Now, this loop of wire is called an armature, and there's actually going to be multiple loops in here, not just one, but simplify it. This is the current, right? So there's current that's moving through this wire around this loop and in, and so that's creating a torque on either side of this loop. Now, this magnet, because it's curved like this, there's actually, this magnetic field is doing some interesting things, right? It's going this way. And so we're not going to see a dead spot in our motor where there's no torque, but also you can put another loop of wire that would go like, say, here and around, and then here. And then you would need another pair of some more brushes here for those armatures to connect to. So what happens when, you can see as this thing spins around, what's going to happen is the current is going to reverse in that loop when it gets up to the top, because this brush is on the negative side and this brush is on the positive side, but there's a gap here, right? And so and that gap is also over here. And so when this thing turns all the way over here, well, now this one is going to get the positive because it's over here, and this one's going to get the negative because it's over here. And so instead of this thing switching back and forth, it's going to continue spinning in a loop in one direction, because we keep reversing the flow of the current through the loop every time the loop reverses its orientation in the magnetic field. So we keep a nice, in this case, clockwise torque on that armature the whole time. Now, speakers, headphones, subwoofers, loudspeakers, they also work on the principle that we're going to have a magnetic field and a changing electric current that's going to exert forces on that magnetic field. So a speaker has a permanent magnet behind it. And in fact, one of the things that was necessary to make miniature speakers, like for your smartphone, was a pretty strong permanent magnet. So once that technology has been improved a lot, then we were able to start making speakers smaller and smaller. So there's a thing called a voice coil on the back of this cone. So this is the frame that's not allowed to move and the magnet's hooked to that. And then there's this cone, which, depending on what your speaker is, these range in things from carbon fiber to cardboard. And then on this cone there's this coil of copper wire, and the signal from your music player, whatever it is pumped into these coils, and this is an alternating current based on your sound wave, and so first current flows one way, then another, and your amplitude might change and whatever. But what that does is this coil of wire creates a magnetic field, and there's going to be either a force of attraction or repulsion between this magnet and this coil, and it's going to drive that speaker to vibrate back and forth. So if what we look at right now, at the instant that this picture is drawing, there is a current coming out of this coil, and so this coil actually, right, it continues out in front and then goes back around, but there's current out of this thing and in over here. And so the force acting on the speaker right now, because that magnetic field is up, is to the right. And then if that current was to reverse direction, then the magnetic field would be to the left. So this is going to create a series of compressions and rarefactions in the air. We're going to get a sound wave out of that. Okay? So motors and loudspeakers are both due to the forces on current-carrying wires in a magnetic field, which is cool. There are some metals that are magnetic at room temperature, iron and nickel. They can become strongly magnetized. The reason for that is because there are regions within those where this is an interesting thing. We know that static charge does not have a magnetic field and is not affected by magnetic fields, but moving charge does create a magnetic field and is affected by magnetic fields. Well, remember, if you have electrons, say you have the electron configuration of iron, and you've got 1s2, 2s2, 2p, whatever. Eventually you're going to get out into the d orbitals. Now here's what's up. We've drawn electrons with upspin and downspin. Well, it's that moving charge that actually gets us a magnetic field, and turns out that the spin of an electron also generates a magnetic field. However, since paired electrons have opposite spins, they create opposite magnetic fields and they tend to add up to zero. But things like iron, they have a bunch of electrons in the d orbitals that are unpaired. And so what happens is they start spinning in the same direction, and then we get a whole chunk of those atoms together that can line themselves up so that all of the electrons are kind of spinning in the same direction, which gives us a fairly strong magnetic field. And if we put it in a strong external magnetic field, that puts a torque on those electrons, and it will actually cause most of the electrons in there to spin in the same direction. Okay, not most of them, but the unpaired electrons to spin in the same direction. And so that's how we get a permanent magnet. And so that's also why when you put an iron bar inside a solenoid, you get a very much stronger electromagnet, because basically you've increased the amount of charge in there that's generating a magnetic field. Anyways, because those domains can all be aligned, we get a nice permanent magnet. But it's also why if you have like a nail and you put it on a magnet, you know it stays magnetic, but if you hit it really hard, it becomes unmagnetic again, and that's because you've just rearranged all those magnetic domains so they're not going in the same direction anymore.